Okay, welcome back. Today we're going to be talking about continuity on R again. Hopefully I make more progress this time. So the first thing, we are going to start off with a definition. We're going to say that F is uniformly continuous on some domain D, right? So here we're assuming F is a function from D to R, and D is just any subset of R. It is uniformly continuous on D if for all epsilon greater than 0, there is delta greater than 0, such that if x1, x2 are in D, and the absolute value, or the distance between x1 and x2 is less than delta, then the distance between the function values of x1 and x2 is less than epsilon, right? And so you can see why this is sort of a stronger assumption than just continuity, because in normal continuity, everything is with reference. You sort of have to have a reference point, right? You sort of say f is continuous at x, and then f is continuous if it's continuous at all such x. But uniform continuity is a definition that it applies across a whole set, right? And you can take any 2 points in this set, so long as they're close together, and then you know their function values are going to be close together, right? So we are going to prove a sort of non-intuitive result that if f is continuous on the closed interval AB, then f is uniformly continuous on AB. And in fact, this result holds for compact sets, right? Compact domains. And we showed 2 lectures ago that a compact set in R is closed and bounded, right? And that's that is sort of, you could take that for definition in R, right? But of course that I don't like that. But right, a compact set, a set is compact if and only if it is closed and bounded, and so you can sort of think of compact sets as being these closed intervals, or at least being contained in closed intervals. And so, right, why is this counterintuitive? We've just said that uniform continuity seems stronger than continuity, but if we have continuity on this closed interval, then it's uniformly continuous as well. But of course this breaks down if you don't have a closed interval, and so I'll show an example of that. Okay, so for the proof, we are going to do proof by contradiction. So if we're assuming it's not uniformly continuous, what does that mean, right? if it's not continuous, then that means then for some epsilon greater than 0, there is no delta for which x1 minus x2 is less than delta implies f of x1 minus f of x2 is less than epsilon, right? And so what we can do here is essentially, since this doesn't work for any delta, we create a sequence of delta. So we take delta sub n to be 1 over n. Or I should say, let delta sub n equal 1 over n. So if x sub n and y sub n are in our interval a to b, then the distance, or so if these are points in a and b, and their distance is less than 1 over n, then we know that f of x sub n minus and actually, so there exists. I should say x sub n and y sub n have to exist, because if such a pair didn't exist, then we would have uniform continuity. So there exists such that the distance between f of x sub n and f of y sub n is less than epsilon, or greater than or equal to. Sorry, it's not less than epsilon, so it's greater than or equal to. Now, since the sequence x sub n is, I'll abuse, actually, let me just write it as a set, is a subset of a to b. It is a bounded sequence. So by the Bolzano-Weierstrass theorem, there is a convergent subsequence, which we will call x sub n sub k, and let's just say this converges to p. Since since a to b is a closed set, p must also be in this interval. Now I'm trying to think if I proved this already. I think I have. No, because I just covered topology on R. Essentially, the idea is that with closed sets, closed sets must contain limit points, i.e., you can essentially think of this convergence, right? Just think of this convergence in terms of balls of some radius, and then you can essentially prove this by contradiction. If P isn't in this closed interval, then it's in an open set, and therefore you can find some ball of some radius which is not in this set, and then it can't contain any of these x sub n sub k, which is contradiction. Then let's look at the y sub n sub k. The y sub n sub k is less than or equal to, so here we're going to use the triangle inequality. It's less than or equal to, so we just plug in an x sub n sub k here. Now we know this is less than 1 over n sub k, and n sub k is getting larger and larger, so this is going to go to infinity, and then this is the distance between a sequence and its limit, so this is also going to, or sorry, this goes to 0, and this also goes to 0, so y sub n sub k also converges to P. Thus, since continuity preserves limits, we have x sub n sub k converges to f of P, and f of y sub n sub k also converges to f of P. Then if we look at the distance between x sub n sub k and f of y sub n sub k, since these two sequences are getting closer and closer to the same point, then they're getting closer and closer to each other, right? So we can write this explicitly using the triangle inequality. There's f of P. And so since these are both converging to 0, this converges to 0 plus 0, which is 0, right? So this contradicts the assumption, or that f of x sub n minus f sub y sub n was greater than or equal to epsilon for all n, right? Because if these things, if this is approaching 0, then at some point it must be less than epsilon, which is a contradiction, and thus f is uniformly continuous. And so let me go back and restate that this in fact works for compact domains, right? Why is that? Well, compact again means closed and bounded in the real numbers, and here we use the fact that it was bounded, and here we use the fact that it was closed. So clearly, as long as you have that it is compact, then the proof works. Okay. All right. Go on to the next thing. The next thing we can talk about is bounded functions. So, definition, f is bounded on D, and just if I haven't made this clear already, I guess like side note, when I say f blah 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 on D, this means that D is the domain of this function, and D is implicitly assumed to be a subset of the real numbers. F is bounded on D if there are M and M and all of them such that M is less than. Do I want to use less than or equal to? I'll use less than or equal to. F of x less than or equal to M for all x in the domain. Right? And now with this definition, we jump straight into a theorem. If f is continuous on the closed interval a to b, it is bounded on a to b. And I believe this would also hold for compact domains. So proof, right? We already know by the previous theorem, f is uniformly continuous, right? Now let epsilon be equal to 1 so that there is delta greater than 0 such that if x1 and x are in AB and their distance is less than delta, then f of x1 minus f of x is less than our epsilon, which is we've set equal to 1, right? Okay, so now we want to let x sub. Essentially, we're going to define a sequence here, x sub n, which is equal to a plus n minus 1 delta. So x sub 1 is equal to a, x sub 2 is equal to a plus delta, and so on and so forth. By the Archimedean property on R, there is n, natural number n, such that n is bigger than the real number b minus a over delta. In other words, a plus n delta is greater than b. And we can also we can choose n such that a plus n minus 1 times delta is less than or equal to b, right? Because obviously, right, if we chose for n equals 1, this is true, right? So it has to be true up until some point, and then after that point it will be greater, right? Thus x sub 1 all the way through x sub n are elements of A to B. Okay. Then we can essentially apply then if x is in A to B, then either, well, then x is in, essentially we enumerate like this, right? Right, we've essentially formed a partition of the interval from A to B. And so if x is in, say, this first one, x1, x2, then we can say that right, and it's important to remember that these have a width of delta. Then we know that the distance between x and x1 is less than delta. So, and it can't be equal to delta, right? Because the only way it would be equal to delta if you were at the endpoint x2, which is not allowed in this set. And so f of x1 minus f of x is less than 1, or we can rewrite this as f of x1 minus 1 is less than f of x is less than f of x1 plus 1. Similarly, if x is in x2 to x3, then f of x2 minus 1 is less than f of x is less than f of x2 plus 1. And we can just go to the last one if x is in this last one, and notice that b, what should I say here? B minus x sub n is less than delta, because right, we chose n such that a plus n delta is greater than b, and this is the same thing as x sub n plus delta. So b minus x sub n is less than delta. So we can apply the same result here. F of x sub n minus 1 is less than f of x is less than f of x sub n plus 1. Okay, so now what we have is that for any x in the interval a to b, we have a finite number, right? There are n compound inequalities here, which means when you have a finite number of numbers with order, right? then we can pick a minimum or a maximum. So then let little m equal the minimum of all the, I'll just do little m since we didn't use little n, right? And this is going over n from 1 to big N, and let big M be the maximum of f of x sub n plus 1. Again, n is going from 1 to big N. Thus, if x is in A to B, m is less than or equal to f of x is less than or equal to m, so f is bounded on m. Okay. I'm not sure if I'm running out of time, but I have just one more thing on continuity, so I'm gonna just go ahead and cover this. And this is going to be the extreme value theorem. So we have a theorem. If f is continuous on A to B, f has a min and max value on A to B. Right? Okay, so the first thing is that f is bounded, right? We've already shown that f is bounded. So f, the image of the domain is a non-empty bounded set. Then let m be, okay, so we're going to work with the maximum value first. The minimum value is similar, you just flip some inequalities. So we're going to let m be the supremum of this set. Then for all k, so for all natural numbers m minus 1 over k is less than m, so it is not an upper bound for f A to B. Thus, there is a corresponding x sub k in the interval AB such that m minus 1 over k is less than f of x sub k, and this is going to be greater than or less than or equal to big M, right? Now the x sub k is a bounded sequence. So by the Bolzano-Weierstrass theorem, which I'm just going to abbreviate as BW. There is a convergent subsequence. X sub n sub k, which converges to some limit value p. And again, since A to B is closed, it's a closed set, it must contain the limit point p. Okay, so hold on. Okay, so I don't know how to name this logical step, but we know that the n sub k are always going to be greater than or equal to the k, right? Because the n sub k are forming an increasing series in the natural numbers, and so they can't be less than their index, right? That wouldn't make sense. So m minus 1 over k is less than or equal to m minus 1 over n sub k, which is less than f of x sub n sub k, which is less than or equal to m. F is continuous at p, right, because it's continuous on this whole interval. P is in the interval. So f of x sub n sub k converges to f of p. And so f of p must also be less than or equal to m, right? Because each value of this sequence, f of x sub n sub k, is less than or equal to m, so you could say it's in the closed set negative infinity to m, close here, and then since it's closed, it must contain the limit, right? So we know f of p is less than or equal to m, but m minus 1 over k converges to m. So essentially we have this sandwiching. So f of p must equal m. And that's it, right? P is a value in A to B such that f of p equals m, which was the maximum of all the values obtained by f on this domain. And you can see that this is also going to be true for compact domains. Why? Because, again, we've used the fact that it's bounded here and here, and we use the fact that it was closed here, so it works for compact domains as well. And right, last lecture we talked about the intermediate value theorem. Here we proved the intermediate, or as the extreme value theorem. And if you put these two things together, you get that if you apply a function f of a, this is going to be a closed interval, which is the minimum of f on A to B to the max of f from A to B, right? Because by the extreme value theorem, we know it obtains a minimum and a maximum, and by the intermediate value theorem, it has to obtain everything in between. Okay. Now, just quickly, I want to before I wrap this up, I want to talk about an example. I promised an example of continuous, but not uniformly. And this would be a good example is, oops, let's see, I want to make this as good looking as possible, is the function f of x equal to 1 over x on 0 to infinity, right? And so this isn't a closed, this isn't closed, right? So we know that not necessarily, it doesn't necessarily have to be uniformly continuous. You can prove it's continuous just by picking any point and then just looking at the region around it, right? But it's not uniformly continuous. Why? Because essentially, remember, uniformly continuous means that if I want the function values to be close together, then I can always get something. I don't know how to say this. If I want the function values close together, I know how close together the input values have to be. And the reason that fails for 1 over x is because of this spike here, right? Essentially, you can think of it as this part of the function gets steeper and steeper. If I want the values of the functions to be, the functional values to be closer and closer together, then since this spike is getting steeper and steeper, the input values are getting much, much closer together, and you can't guarantee that delta, right? The delta is going to be the corresponding, the epsilon is going to be the same everywhere, but the delta value will start failing as you go to the left of the graph. And essentially, a way you can think about uniform continuity is that the derivative or slope, since we haven't talked about what a derivative is, the derivative or slope is bounded, right? And we can see that because we have f of x1 minus f of x2, and we have f of x1 minus x2, right? This is the absolute value of the slope, and we know that we can always, we essentially, uniform continuity means we can always bound this by some m, which is equal to epsilon over delta. If I pick an epsilon, I can pick a corresponding delta. That always works. And here we see why that fails, because 1 over x is getting steeper and steeper, right? The slope is going to infinity, and so it's not uniformly continuous. So anyway, that's it for this lecture. I'll see you next time.